Alright, these are your video lesson notes for 1.1, 1.2, and 1.3. Just discussing relations and functions. Most of this you have seen before, it's just been a long time. So relations are anytime you relate two items to each other. So generally we would see that as ordered pairs, since we relate an x value to a y value, similar to what you're seeing in the mapping diagram right here. Definition of a function is simply any function where each x element belongs to only one y element. So remember that your domain are your x's and the range are your y values. So if you look at the first example here, the set A would be the domain values, set B is the range values like x and y. As you look at the x values, you can see that each x value that we have only has one output or one range value. So that's why this one is a function. But if you compare that to number 2, if you see a value of 1 goes with 1, a value of 1 goes with -1, so because the value of 1 has two different outputs, that would make this not a function. So you can't repeat your x values. It's kind of an easier way to look at that. So when you do them as ordered pairs, like what you're seeing right here in part B, it's just the same idea. They're just written as ordered pairs instead of a mapping diagram. So really all you're looking for is, do we repeat any of the x values? So as I look at this, -6, 5, 2, 6, and 4, those are all different. That's why this is a function. The y values really don't matter for that, as long as the x values don't get repeated. But if you compare that right here with part B, this has an x value of 3. This one also has an x value of 3, which is why this is not a function. 3 gives two different results. If for something to be a function, I need to plug in an x value and not get two different results. If you think of that in terms of like operating a machine, if you compare that to an equation, if you put something into a machine, you would expect one specific result every single time. If I put something into a machine and it's giving me different outcomes, even though I'm putting in the same value, we would say this machine is not functioning properly because I would be getting different results for the same input. So just like on this part here, I have the same input, I'm putting in a 3, but I'm getting two different results. So we would say this machine is not functioning. Again, option C, we would say this is a function because the x values are all different. So that one is good. That's the way you tell whether or not something is a function if you actually have all the data values. But if you don't have the data values, like with just an equation like this, x plus 3 or whatever we have for each equation, you don't have all the specific values. So one of the simple ways of telling whether something's a function or not from just an equation is with the vertical line test. And I know you guys have seen this before, but again, it's probably just been a while. If we were to graph y equals x plus 3, that's just a linear graph, right? Think of y equals mx plus b. It's starting at 3, that's the y-intercept. I'm using a slope of 1, so we're going up 1 over 1 to get each value. That's where this line is coming from. The vertical line test simply says, if I can draw a vertical line anywhere on my graph and only hit one point, then it's a function. If I can ever hit more than one point, then it's not a function. And that's what you're seeing right here on number 2. If you were to graph this scenario here, and if you're trying to graph this by hand, you would probably just take the square root of both sides. So you would get the equation y equals plus or minus the square root of x. And if you were to graph that, this is what you would see. But you can see that this would fail the vertical line test because I can draw that vertical line right there and hit the graph twice. So that is not a function. And again, just another example with number 3, absolute value graphs. Everywhere on here that I can draw a vertical line would only ever hit this graph once. So I know that it is a function. It passes the vertical line test. So going down here to the last part, just being able to identify domain and range, mostly from a graph, is simply to look at the domain as your x values. So from this graph, if I just start with the domain, I'm just looking from left to right for the x values. So the farthest left is -4, the farthest right is positive 3. So we would say the domain of this graph, it goes from negative 4 to positive 3 from left to right. And so that's what you're seeing right here. We'd have to use the inequalities because that way we include every possible value between negative 4 and 3 as well. So we're putting the x is greater than or equal to negative 4, less than or equal to positive 3. You do need to include the equal sign simply because these are filled in. So you need the equal sign to show that we are also including negative 4 and 3. You'll see the difference on that one over here where we have something that's not included because it's open. The range on this, same process, but you're going from bottom to top. So the lowest y value that we see is negative 3. The highest y value that we see is 6. And there are no gaps in between that. It is inclusive from negative 3 all the way up to positive 6. So this is what we would show for the range. This one's just a little bit trickier with the drawing, but just keep the same thing in mind. For domain, I'm just going from left to right. So the farthest left that we go is negative 5. The farthest right that we go is positive 6. That should say positive 6, not 1. Anyway, so from negative 5 to positive 6 would be the domain, but notice the use of equal signs on this. So this one is filled in, so we are including negative 5. So we would say x is greater than or equal to negative 5 because we're including it. But on the right side, we would say that it is less than 6. Because it's open, we're not including the 6, so there's no equal sign on that. This is continuous from left to right. Everywhere from negative 5 to positive 6 has a value that's filled in, so we're good with just one inequality on that. The range from bottom to top, the lowest point's negative 2, the highest point's positive 3, so that's how we'd show the range of that graph. Even though there is an opening here, so we would say this graph is discontinuous at this point. Even though it's discontinuous at 1 here, it's continuous at 1 here. So as long as you have a point for a value of 1 somewhere, it can still be included. So that's why we're okay with just this one inequality statement that you see right here. On number 3, we're seeing what happens when you have an asymptote. Remember that an asymptote is just a boundary line. It's an area that the graph approaches but never actually gets to that value. So as you see right here, this asymptote for y equals negative 3, as you go farther and farther and farther to the left, or we could say as x approaches negative infinity, our y values get closer and closer to negative 3. You'll never actually get to negative 3. You just forever get closer and closer to it the smaller you go. Just like on the right side, we have the vertical asymptote for x equals 7. So as we go farther and farther, or as we get closer to as we get closer to positive 7, the y values simply increase. So we're approaching 7, we'd never actually get there. So this would be a value where you can't put in negative 7, or you can't put in 7 for x. You can just get closer and closer to it. So this is what we would say for the domain. All right, domain is just the x is everything to the left of that number, not including 7. And for the range, everything above negative 3, not including negative 3. And there are times where you're going to be asked about asymptotes, vertical and horizontal. So all right, they're always written as an equation. So those are just good to keep in mind for what those are. And the last part, kind of some notation issues and some pretty simple substitution down here. If I have the equation y equals 3x minus 7, just a notation that we've seen before, it can be written as f of x instead of y. It means the same thing. Anytime you see f of x is the same thing as a y value. Simply means that if I were to sub in a number for x, this is my result, is the y value. So if you take a function like this one, if we were to say f of 2, simply means I'm going to replace x with 2. So f of 2 is equal to 5 times 2 squared minus 2 times 2 plus 3. And so that's the work that you're seeing right here. And if we just clean that up, it comes all the way out to be 19. Again, just a little more understanding of the notation. F of negative 6 simply means I look at the f function and I replace x with negative 6. And that's what you're seeing right here. On the right side, again, all you're going to need to do is sub things in. I'm going to replace f of x with this. I'm going to replace g of x with this. So replacing f of x plus 4 times g of x. And then you just simplify that as far as it can go. This is not an equation. There's nothing to solve. It's just an expression. So you just simplify it as much as possible. This one, however, is an equation because of the equal sign, so you are actually solving for x on this one. But again, it's just really substitution. I'm going to replace f of x with the 17 minus 4x. Going to replace g of x with half x plus 3, and then just solve for x. So again, do understand the difference between simplifying an expression versus solving an equation. So this one we actually get a solution. This one we just simplify it as far as we can go. And that's it for our first lesson.